Good morning, my dear warriors, and I wish you all a very happy Diwali to all of you. And it's slowly started to get cold. Time to put on some jackets also, finally. Welcome aboard, my dear lovely warriors. Wish you all a very happy Diwali. Already have lit the chat box with the fire emoji. Thank you so much. Celebrations have started digitally already. Glad to know that. Very good, Krishna. Hi, Evening Star. Hi, Jasmine. Hi, Atluru. Hello, Harborine. And you can hear some noise in the background too. I just hope I'll be able to conduct the class. Okay. So today's topic, alternating current, chapter number 7. We have already crossed 6 chapters. Today we'll be done with chapter 7, guys. I mean, literally half of the syllabus almost done. And with me, your Capto Shreyas. This is your NCERT line by line decoded series where it will not only help you for your CBSE board preparation, but also these series will help you for your competitive exam preparation. And my name is Captain Shreyas, your master teacher, teaching for more than 13 years and done his research from IIT Bombay, graduated from IIT Nagpur, teaching more than thousands of students and mentoring them. Good evening. Happy Diwali. Happy Diwali. Thank you so much, Disha. Thank you, Krishna. Thank you, Evening Star. Thank you, Arluru. All the warrior Pandus. Thank you so much. Means a lot. So, this chapter is very interesting because I'll just show you the introduction. This thing is there. And it starts with Nikola Tesla. It's a very interesting story. 100 years roughly back, Thomas Edison. What did Thomas Edison do? Put it in the chat box. What did he do? He invented something, right? What did he invent? He invented something. Yes, he invented the bulb. And yes, hello Tanuja. And during those times, they had direct current. Direct current is basically that current which you get from your adapter. Like, oops, where is my adapter? It's gone somewhere. It's not there. Anyways, I can't find it. So that adapter, that mobile charger, what you get is basically adapter. It gives you direct current. Even these things, these batteries, what do they give? They give you direct current, right? They give you basically direct current. Yes. Then it was Edison who told, it was Tesla who told that actually you should not use direct current, you should use alternating current. Alternate means once this, once that, once this, once that, once positive, once negative, once this way, once that way. That is alternating. You keep changing. You should use that. It is better to transmit it easily. It is easy to convert it. It is easy to change the voltages. There are little power losses, hardly any heat energy is lost, so it is better. But Tesla was like that Pavam guy who is very sincere, who is very dedicated, who is very research oriented. Edison was a business minded person. Edison was a businessman. He had already established his business in direct current. He felt threatened and then he ran a false propaganda 100 years back saying, you know what, AC is bad, you will get shock, you will get electrocuted, you will die if AC current enters your body. Although it was true, but it was very safe if you pass it safely, if you have insulated wires and you manage it properly, it was actually good. But then because of this false propaganda, what happened? People thought, oh my God, Tesla, he's trying to brainwash us, he's trying to electrocute us. People are thinking that he is some scary guy, and they believed Edison. And Edison, being the businessman, he earned a lot of money during that time because of, direct current. And then after many years, after Nikola Tesla died, then people realized actually what he said was correct. We were fools. And now in our households, everywhere, what is there? Alternating AC current is there everywhere. So sometimes people realize it little bit late. In fact, he dreamt about transformers. He dreamt about many devices in his mind, and the next day onwards he started working on it and it actually worked. So he said that he used to do something called as lucid dreaming, lucid dreams, and he was, able to invent so many machines like the motors, the transformers, and so much more. So Nikola Tesla, the main guy behind the alternating current, the usage of it, and the changing of the voltages, which is the transformer, all of this. So huge, massive respect for Tesla. Oh, now the company name is Tesla, but it is not by Nikola Tesla, it's by Elon Musk, so don't get confused. So this is what is basically there in the introduction part. All right, you can see this was 1856 to 1943, that's nearly 100 years back. All right, even he made one coil saying that you can harness the energy from the surroundings. You don't need batteries, you don't need generators, you need not burn coal, you don't need nuclear energy, you don't need hydro energy, you don't need wind energy, you don't need tidal energy. You can harness the energy from the surroundings. But people thought this is going to threaten their business. Then how will I sell coal? Nobody will buy my coal. How will I sell my diesel or petrol? Nobody will buy that. How will I sell anything? So people got threatened, and it is claimed that his lab was burnt down and all his inventions also caught fire and it was destroyed. Okay, so nobody knows how that mechanism worked, how he was able to harness energy for free from the universe and convert it into electricity. Nobody knows till date. But again, conspiracy theories believe that the equipment did not get destroyed, but some secret agency actually captured those devices and stored it somewhere, and only they know how to harness that energy. We don't know what is the truth, but this is just conspiracy. All right. So starting off with alternating voltage applied to a resistor. So first of all, let me give you some examples of AC. So some examples of alternating current, all right. So let me just give you some of them. So imagine something like this: up, down, up, down, up, down. One's positive, one's negative, one's positive, one's negative, one's positive, one negative. Or like this: positive, negative, positive, negative, positive, negative. Or something like this: positive, negative, positive, negative. Or maybe just like this: positive, negative, positive, negative. Now, what does this positive and negative mean? What does this positive and negative mean? Understand. Positive means that in case, let's say for example, you have a circuit. If the current is going one direction, it is considered, let's say, positive. If the current is going like this, and if the current reverses the direction, then it is negative, if the current goes in the other way. So positive, negative over here just stands for the direction, that's all. Okay, so that is why alternating, one's clockwise, one's anti-clockwise, one's clockwise, one anti-clockwise. That is basically called alternating current, a current which reverses the direction, periodically. It reverses the direction periodically. So if you ask me what is the period, well, it is from here to, it is basically from here to here. This is one time period. You can even go from here to here, one peak to another peak. This is also one time period. From here to here, it is one time period. Or even from here to here, that is also one time period. Even from here to here, that is also one time period. Or from here to here, that is one time period. Is there any relationship between time period frequency and angular frequency? Yes, this f, which is just your frequency, this f, which is just your frequency, my dear warriors, frequency, f is just 1 by the time period. Not just that, there is another term called as angular frequency. Angular frequency, if you have heard this term in SHM oscillations and so many other places, omega is nothing but 2 pi into f, which is also the same as 2 pi, because f is 1 by t, it is 2 pi by time period. The unit of omega is radians per second. The unit of just frequency is just hertz, is just basically hertz per second, because time period, the unit will be just seconds. Time is measured in seconds, frequency is 1 by second, which is a hertz, and angular frequency is 2 pi by t. This is radian, this is second, so radian per second, that is your omega. I hope this is absolutely clear. Another parameter which you should know regarding this is how high it goes and how low it goes, that extent till which it goes up and down on either side, that extent till which it goes up and down on either side like this. This thing is basically called as the amplitude. This is called as the amplitude. So amplitude is the maximum variation in the current or the voltage, amplitude. Sometimes also it is called as the peak value, peak or the amplitude. A is how much variation is there from its standard mean average value. I'm standing here, Shreyas Sir is standing here, Shreyas Sir goes here and then goes here. Some people have that habit. When they are thinking about something, they will go like this. They are worrying, how much marks will I get in NEET exam? Okay, will I get 700? Will I get 650? Okay, if I study for 5 days, if I study for 4 hours per 5 days, and then I will complete this chapter, and I'm thinking something. So, from here, I went 2 meters here, I went 2 meters here, 2, then 2, then 2, then 2. So, from my average position, I moved this side 2 meters, this side 2 meters. So, my amplitude is 2 meters. So, the variation which occurs from the standard average value. Correct. Crystal clear, Atluru, Sneha, very good. Yes, Nicola. Tesla is also in the chat box. Wow, so cool. Very good, Disha. Awesome, awesome. Krishna. Let's move ahead. Now, what happens? Oh, by the way, what is the symbol for alternating current? You should know this. The symbol for an alternating current source, it is like this. This is a symbol of a alternating source. That means, let's say you have a plug point in which you put your plug and current is coming from there, or generator is there which is giving electricity, or some power plant is there. So this is the source of the electricity, but this is alternating source. For DC, remember, it was like this. You put a big line, small line, big line, small line, negative and positive. So this is for DC. For AC, it is one circle with line like this. Who is positive and who is negative here? Can you guys quickly think and tell me who is positive and negative? Smart answer. All the smart kids will answer very quickly now. Which side is positive, which side is negative? Quickly tell me in the chat box. Very good. Yes, nothing is positive, nothing is negative. It keeps changing. Once this is positive, this is negative. Next time this is positive, this is negative. So it keeps alternating. AC, correct. So it is not like one side is positive, one side is negative always. It keeps alternating. It keeps changing. Correcto, perfecto, amazingo. Moving ahead. What happens when you connect an alternating circuit to, you can see this is a source, to a resistor? There are some interesting things in this paragraph. I will just probably, mark some important formulas right over here. Let's say this is the voltage difference, this is the current, where I is equal to this. This is one important thing. Let the potential difference be also called as the AC voltage, where Vm is the amplitude of the oscillating potential. Okay, applying the Kirchhoff's rule. Okay, this is what we get, and this is the equation in Ohm's law, works equally well for both AC and DC. Pure resistance and the current fluid is given by this are plotted. Note in particular both V and I reach 0, minimum and maximum at the same time. Clearly the voltage and the current are in phase with each other. These are the important lines in this. Let me explain. So when you are attending any of these classes, keep your NCERT also open, because I follow exact NCERT line by line, and you can start marking exactly the same things in your NCERT. Unfortunately, I cannot share this with you because of copyright restrictions, okay, of NCERT, but other than that, you can directly start marking it in your NCERT. Now I will explain this to you. What do I mean by this? That is very important. Let us understand this, guys. See, you have an source, AC source, and then you have a resistor right over here. This is your AC source, and what happens is now there will be some current which will be flowing in this particular circuit, and also there is some voltage which is generated by this particular source. There is some voltage or EMF which is generated. Either you use the symbol E or you can also use the symbol V. One and the same thing. Don't get scared if somebody uses E. Okay, it is the same as the voltage difference. Let's say I call it V also. Doesn't matter. Okay, now observe. Imagine the source produces a voltage. The source produces a voltage V which changes with time, and it looks like this: V0 sine omega t. Why this is like this? This is the equation of an oscillating, pulsating, sinusoidal, alternating, whatever name you want to call, voltage. Sine. How does the sine graph look? Positive, negative, like a bumpy ride, speed breaker type. Sine voltage, sine graphs always look like that. So what does this mean? This just means that if somebody decides to draw a graph versus time of the voltage, this particular graph will look something like this: positive, negative, positive, negative, like this. And the maximum value reached will be V0, and here this side will be negative V0. This will be positive cycle, this will be negative cycle. So plus V0 to minus V0, it will keep oscillating, and needless to say, from here to here is basically one time period, which is 2 pi divided by omega. Remember, omega was 2 pi by t. I just gave it to you. Omega was 2 pi by t. So t will be 2 pi divided by the omega. Hence, this is one time period, one crest and one trough, one peak and a valley, one up and one down, one positive and a negative. That is one cycle. So that is time period. That will give you omega, which you substitute here. It looks like the equation of simple harmonic motion, or a sine graph, or basically a wave, or a graph which goes up and down periodically like a sine function. Yes, this is why voltage is V0 sine omega t. This V0 stands for the amplitude of the voltage. Amplitude of the voltage. This over here is the voltage. This is the voltage at any instant. This is the voltage at any instant. That t over here represents that instant of time when you are calculating it. Omega have already defined and told you before this. Is this clearly understood how this equation is written down? Everyone with me? Okay. Now let us apply Ohm's law. Let us apply Ohm's law. Ohm's law, or basically Kirchhoff's law, whichever you want to apply. Kirchhoff's law, whichever law you apply, my dear warriors. That applied voltage at any instant should be the current, should be the current multiplied by the resistance. Should be the current multiplied by the resistance. Should be the current multiplied by the resistance. Therefore, the current value will be nothing but the voltage divided by the resistance. But wait a minute, I already know what is the value of the voltage. The value of the voltage is V0 sine omega t, and the resistance as it is stays over here. V is nothing but V0 sine omega t. So V0 sine omega t is put here, resistance is staying there as it is. So how about writing this entire equation in a simpler form? I is equal to, this is a constant, this is a constant, write it as I0, I is equal to nothing but I0, and this same sine omega t, I can put it over here, where I0 is maximum amplitude of the current. The amplitude of the current is nothing but your voltage amplitude V0 divided by the resistance. So this I0 is nothing but the current amplitude, the amplitude of the current amplitude, the current amplitude. Is that right, my dear warriors? Understood till this point over here? Very good. All these formulas again they're over here, but it's just that I'm doing this for you so that you see how it is done. Because when a text is presented, sir, what to look, up, down, sir, I didn't understand. You explain it line by line. That's why Shreyas Sir is coming over here with a blank screen with the NCERT text, underlining everything for you. Okay, this is the maximum variation in current. Can I plot the current over here? Yes, of course. See, voltage was a sine graph, even the current is a sine graph, meaning the graph of the current will exactly match this one over here. This will also go up and down, up and down, up and down like this. This will be plus I0 and this will be negative I0. That's why current amplitude. I hope you can see that. Now, from this graph, don't you see, when this is going up, this is going up, this is going down, this is going down, when this is 0, this is 0, this is minimum, this is minimum. Imagine I am Pandu and besides me there is Champa. Some Champa is there. Pandu goes here, Champa goes here. Pandu goes here, Champa goes here. Okay. Pandu and Champa both go together. Pandu and Champa both go together. Okay. But the extent till which they go is different. When Pandu goes this much, Champa only goes this much. Pandu goes here, Champa goes here. But their amounts are different. That's okay. But they are in the same situation. When they are left side, both are lefts. Pandu is left, Champa is right. Pandu is left, Champa is also left. Pandu is right, Champa is also right. Pandu is 0, Champa is also 0. So both of them are going together. They are said to be in the same situation. Another word for the word situation is phase. Phase. I am in a very good phase, bad phase. So both the current and the voltages are in the same phase, like constructive. Yes, correct. So I can say that both of them are in the same phase. Same phase. Sometimes the word used for that is a delta phi. This is 0. This delta phi happens to be a term called as the phase difference. The difference in their phases is 0. That's why same phase, or you can also use the word in phase. In phase. This is also okay. Or the word in phase. This is also perfectly okay. Is this clear, my dear students? Understood? Okay. Awesome. Great. So that is what has been mentioned over here. All right. Now, in the next part, they do some calculation for the power. The fact that the average current is 0, however, does not mean the average power is summed as 0 and that there is no displacement of the electrical energy. That is not true. That's what they say. However, this word does not mean, is very important. Average power is 0. That is not true. And no power is dissipated. That is also not true. In fact, what is true is that as you know, Joule's heating is given by I square R, does depend on I square, which is always positive, whether it is positive or negative, and not on I, very, very important, and not on the value of current. Thus, Joule's heating and dissipation of electrical energy when AC current passes through a resistor. They have done that calculation over here. One important value which you must know is the value of sine square omega t. Average is half. Okay. Cos to omega t average is 0. Okay. And finally, they get some equations over here and they block it. Okay. Where Vm is this. Okay. And then over here, this household line voltage is a RMS value with a peak voltage of 311 volts. Okay. And same of the DC case. This shows the advantages of introducing a concept of RMS value. In terms of RMS value, the equation of power, etc., is the same as those of the DC case. Okay. And again, they have put over here the current RMS value. And then another important thing which you should better know, it's there in the side footnote over here. Okay. So these are the important things. I have just underlined them. Now I will start explaining this to all of you. Okay. Just imagine that you have a resistor like this, and through that resistor, this particular current is going. This current happens to be I naught sine omega t. It is sometimes positive, sometimes it is also negative. Now, if you ask me what is the power which is lost in this resistor, one might think, sir, if you look at these graphs, if you look at these voltage sine graphs, or even if you look at these graphs over here or here, you will see one thing: how much ever positivity is there, that much negativity is there. How much ever positivity, that much negativity is there. So if you ask me what is the average value, average or mean value, what will the answer be? The answer will be a big fat 0, isn't it? The averages will be 0. Agree or disagree, my dear warriors? Tell me. Because how much ever positive I go, that much negative I go. That means the average will be a big fat 0. Correct. Oh, so sir, the current or the voltage average is 0. So from this, the average value, which is also symbolized like this. Do you remember these triangular brackets? When you put triangular brackets, means average. So if I say marks of a student, and if I put this, means average marks of the students. Correct? If I put height and I put this, average height of the students. So this is average current is obviously 0. But there is a but. What is that but? The but is the average power is not 0. You will be like, sir, why sir? Average current is 0. Why is average power not 0? The reason for that comes from this logic. See, power at any instant is I squared into R. This is the power loss at any instant, I squared R. So think about it, whether the current is positive or whether the current is negative, the square of the current will always be positive. If every time the power is positive or maximum 0, so how can this number ever be negative, which means how can this number's average be 0? Think about it. Even if the current goes like this, energy is lost. Even if the current goes like this, energy is lost. So it's not like if the current goes like this, energy is lost, and the current goes the opposite way, energy is being, taken back. It's not like that. You go like this, it gives out, it goes like this, it takes back. No, it does not give and take, it just gives and gives and gives, and it loses that energy no matter which direction the current goes. Hence, the average is not zero. This can come like a reasoning question. Is that okay, my dear warriors? Is this understood? Oh, clear? Oh, happy Diwali, Pranav. Evening Star, I know you can hear the pataka, the Diwali dhamaka sounds in the background. Thank you so much, Pradeep. Okay. So, what happens is when you want to calculate the average, when you want to calculate the average power loss, this is your average loss of the power, then R is not changing, resistance is constant. So, it will be basically you find the average of I square and multiplied by R. Now, you might be wondering, sir, how do I find I square's average value? Well, you substitute the value of current. It is basically I naught square into sine square omega t. Okay, this guy's average you have to find. This guy's average you have to find. Instead of I have put I naught sine omega t, but because of that square, I have squared both these things. I naught is a constant. I naught is a constant, so bring it outside. I naught square. What is remaining inside? You are remaining with sine square omega t. You are remaining with only sine square omega t, correct, into R. Now, you will be like, sir, what is the average of sine square? This is what they have mentioned in the footnote. Cos 2 omega t's average is this. You have to remember, and sine square omega t's average is half. You have to remember this. Remember this for every problem. Sine square, cos square, remember this. I will write it down for you, what and all you are supposed to remember also. See this clearly. Sine omega t average is the same as the average of cos omega t, which is 0. Whereas, if you even take sine 2 omega t or cos 2 omega t average, that is also 0. What is the reason for that? The reason for that is when you draw any of these graphs, when you draw any of this sine or cos omega t graph, sine graph is like this. So, how much ever positive, that much negative. How much ever positive, that much negative. If you draw a cos graph, the cos graph goes like this. I mean, I can draw it below over here. The cos graph goes like this. It starts from highest value, goes down like this, it goes like this, goes like this, goes like this. So this is basically one cycle. This is the next cycle. So how much ever positivity is there, that much negativity is there. So average values, sine 2, cos 2, sine omega, sine 3 omega, sine cos 5 omega t, whatever it is, always their average values are 0. Keep that in mind. But the moment you take sine square, the moment you take square of the sine, this will go up. Square of the sine, this will go up. It will be like this. It will be like this. So this is sine square or basically cos square graphs. So that is the reason why you will see the average value of sine square omega t, which is the same as cos square omega t, that is not 0, rather it is half. So the average value is basically somewhere over here. This is basically half. This is what you should know. Is this absolutely clear? Now you will never forget it. It's not difficult to remember. If it is pure sine or pure cos, it is 0. If it is sine square or cos square, it is always positive. It's above the horizontal line. Hence, it is having an average non-zero value, which is half. Clear, oh, Sneha? Very good. So that is the reason why I can just put over here this as I naught square multiplied by half multiplied by R. But I do not like this. I like this average power in a special way. I square R. I don't like this number 2. How about writing it as I naught by root 2 whole square multiplied by R. So now what I can define this as, this value I naught by root 2 is now called RMS, IRMS square. So where I will put over here, where IRMS root mean square is I naught square by, sorry, not I naught square, I naught by root 2. Maximum by root 2. 1 by root 2. Root 2 value is approximately 1.414. If you take 1 by 4.414, you will approximately get 0.707 times of I naught. This is approximate value that you get. Yeah, this is something again you should be aware of. Okay, 0.707 I naught. This is called as RMS, root mean square value. So why did we do this? Why did we do this? Usually power is written as I square R. So if you notice, in DC circuits, we use this formula I square R because the current is constant. So now we have got one current which is called IRMS, behaves like a constant current, just like the DC formula, which produces the same power loss in that resistor. Observe this carefully, guys. What do I mean by that? Imagine this. Our current was changing like this, okay, and the maximum value was I naught. What I have got now is an imaginary constant current whose value is IRMS, which is I naught by root 2, which is almost 70%. 0.7 is 70% of I naught. So this IRMS is that constant direct like current, which produces the same power as of the alternating current, So RMS is that constant current which produces the same loss as that of that varying. Something is going up and down, up and down, up and down. You forget that up and down. You give me one constant value which gives the same loss as that up and down current. That is RMS current. Is this clear, my dear students? The definition of root mean square or RMS. Root mean square or RMS. Similarly, you can also say, you can also say that our RMS voltage, root mean square voltage, is nothing but our maximum voltage divided by root 2, which is approximately 0.707, 70% roughly of V naught, approximately. Is this clear? Next important thing, unless mentioned otherwise, keep this in mind, unless mentioned otherwise, all voltages and currents in AC are RMS only. You never give the maximum value. So for an example perspective, when I say household voltage is 220 volts. What is this 220 volts? It is RMS value. Yes, it is already RMS value. So 220 is the maximum voltage by root 2. Therefore, the maximum voltage is root 2 times 220, which is approximately 1.414 times 220, which comes out close to 310 volts. Yes, the maximum voltage which your household circuits get is plus 300 minus 300, plus 300 minus 300. But if you take that constant voltage which produces the same energy equation, that answer will be 220 volts. Got it, everyone? Crystal clear? Clearo? Everyone with me? Alright, if you have forgotten to smash the like button, do that right now for your Vedantu English channel right away. Yes, in case you have forgotten. Cool. Awesomeness. Awesomeness. So this is what has been explained in a different way, but I mean, I have made it very, very simple, lucid, easy to understand for you. Otherwise, you will be like, sir, what the hell happens here in NCERT, sir? Maybe you should only write NCERT. I wish I could write NCERT. Okay, a light bulb is rated 100 watt for 220 volts. Find the resistance of the bulb, the peak voltage of the source, and the RMS current through the bulb. Okay, see guys, clearly in this 100 watt, that is basically your average power, 100 watt bulb. When you put a bulb, it is written 2 watt, 5 watt, 100 watt bulb. Voltage, so that 220 volts is basically your RMS voltage. RMS voltage. Okay, so if I want to find the maximum voltage, find the resistance of the bulb and etc. Okay, so first of all, if I want to find the maximum voltage, that divided by root 2 is RMS. Therefore, maximum will be root 2 into VRMS, which is 1.414 into 220, which roughly comes out to be as 310 or 311 volts. Okay, 301, 311, that's okay. If you take exact value, comes very close to 311 volts. I had approximated it to 310. Okay, so don't get scared, sir, you wrote 310 here, why 311 here? If you do more calculations till the third decimal, it will come to 311 volts. It's okay. Approximately we get the answer. All right. So having said this, I got the maximum voltage, the peak voltage of the source. Option B we have done. Okay. What about the other question? It says, can you find the resistance of the bulb? See, power is V square by R, I squared R. You can use any of this formula. So when I use V squared by R, which voltage is this? It's always the RMS voltage. So therefore, the resistance will be V RMS square divided by the power. So RMS voltage is 220. So 220 square divided by the power, which is 100. So this value of resistance comes out to be as 484 ohms, because 22 square is 484. That is the resistance value. Similarly, another question might be, can you find the RMS current? When you use V is IR, then remember, if this is peak, this is also peak. If this is RMS, then even this is also RMS. This is maximum, this is maximum. This is average, this is average. This is RMS, this is average. Same kind should go together. This can't be maximum, this is RMS. That is not allowed. This is average, this is maximum. Not allowed. Average, average. RMS, RMS. Ram, Ram. Sita, Sita. Gita, Gita. Like that it is. Okay. So, RMS voltage is 220. Current RMS not given. We have to find. Resistance 484. Therefore, RMS current will be nothing but 220 divided by 484, which comes out as you can see over there, 0.454. 0.454 amperes. 0.454 amperes. That is your RMS current. Got it, guys? How to solve this particular question? Everybody with me? Very good. Next, representation of voltage and current and etc. in phasor diagram. This is a very important topic. So I'll tell you, see, anything which oscillates, anything which oscillates can be represented in a much better way. I'll tell you what do I mean by that. Everybody knows the earth is round. Nobody believes the earth is flat, right? Over here, hopefully. We know earth is round, like this. Okay? But this is a model of the earth. The earth is very huge. I can't show you the earth. You are staying on the earth. You can see down, you will see the earth. This is how the earth roughly looks like. But when you have to show any place, any country, any continent, any city, etc., okay, or just the globe itself in the atlas, how does it look like? It is shown like this in the map view, right? So if you open the atlas, let's say I open the atlas, oops, yes, atlas over here, atlas globe, yes, this is how it looks like, see? Wow, this is how the atlas looks like. This is our, yeah, this is how it looks like. But does that mean that the earth is flat? This is just a representation of whatever is there here on a 2D dimension, right? This is 3D, this is 2D. This is just representing it. You don't have to take it literally. Sir, so can I go from Canada to Russia like this, sir? It is straight line, sir? No, actually, if you see over here, Canada to Russia is not a straight line. It is a curved line. It is an arc. You have to go in an arc. Understand that. Making sense, everyone? Correct? So it is just a representation. Correct. So, same way, any varying quantity, anything which goes up and down, up and down, up and down, can be represented in something called as phasor, which has similar characteristic. Like in the globe, there was Russia. Here also we have Russia. Here we have something, ocean is there, here, there. So same thing is there on that atlas also. Similar identical quantities, but they are shown in a different way. So understand this very, very clearly, my dear students. Oops. If this graph goes like this, sometimes the graph might go like this. This is like the cos graph, this is like the sine graph. All these graphs are in something called as in the time domain graph, because the horizontal axis is the time. The horizontal axis is the time. Then you have something called as the phasor diagram. Phasor diagram. In a phasor diagram, you have just one reference line. That's it. You just have one reference line. Phasor diagram. You just have something called as the reference line. This is your reference line. This is your reference line. And you show a vector like thing which is called as a phasor. You show a phasor which looks like an arrow, a ray, which keeps rotating with the same speed as that of the oscillation speed, whose length is same as the amplitude, and whose projection gives me this, meaning, just observe this very carefully. I will show the phasor like this over here. At the start, at the beginning, when the time was 0, the value was 0. If you draw a line like this, it falls over here. After some time, maybe you go here, after some time, and if you just probably draw a dotted line, maybe this is what you get. So this is the value that you get after some time. After some more time, maybe you reach here, and if you draw the shadow or something called as the projection, you reach here. So this is the value after some more time. You wait for some more time again, you will see that you will reach here, and this is the value that you will get after some more time. Again, after some more time, you wait, you will go over here, and the shadow, of course, will, the shadow, of course, will go like this till here, and you can see this particular value over here. So, you can go even further down like this, not a big deal. You can go down like this also, okay, like this over here, and you will see the downward values as well over here, and then the maximum value down like this over here, like this. See if you are able to visualize, as this rotates, their shadow or their projection means if you draw lines, if light were to fall here, where will it be on this wall or in this diagram? So if light came from here, this point shadow will be over here, so along this line. This point's shadow will be along this dotted green line. So that is the meaning of shadow or the projection. So how much is the component in the y direction, or how much is the projection, or how much is the shadow, or how much it is along this line, I can get it by drawing these lines. So wherever this is shows me the current situation of this graph. If it is here, I've just started. If it is here, it has reached here. If it is here 90 degrees it has covered, then it has reached the maximum. If it covered 180 degrees, it has completed half the cycle. If it completes 360 degrees, it has come back over here. If it has completed 270 degrees, it has reached the bottom point over here. So that is why this is called as a phasor diagram. Are you able to visualize this now? Same thing I can also do over here. Slightly better diagram I'll have to draw. I'll just try it. Don't worry. Initially, I will be in this situation here, like this. After some time, let's say here, like this, and the graph that I will draw, oops, like this. So initially yellow line, you can see I was here. Then after some time, you can see I was here. After some more time, you can see I was here. After some more time, again you can see I was here. After some more time, you can see I was over here. After some more time, you can see I was again over here, correct? Again after some more time, you can see I was over here. Again after some more time, you can see I was over here, right? And again after one complete revolution, you can see again I was over here. So this is how it goes up and down as this thing rotates. So a phasor diagram gives me the situation of a oscillating waveform. Gives me a situation or the phase or the situation of the oscillating waveform. Correct? Yes, correct. So now from this I really understand what exactly is going on. You need something called as the reference. And then you have something called as the phasor. This is called as the phasor. A phasor has a length of the amplitude of the graph. It has the amplitude of the graph as the length. So this becomes your amplitude. It also will rotate with some angular speed. The angular speed of rotation is the angular frequency of the graph, is the angular frequency of that particular graph. Also, that is, you can say the time period is the same. It makes sense. In 5 seconds, if it completes one revolution, So in 5 seconds, it will complete one wave. If it takes 0.2 seconds to complete one entire wave, it will also take 0.2 seconds to complete one revolution over here. So that is what is there in your phasor diagram. Now imagine this. You have a graph, and there are two waveforms in it. Meaning, let's say one is like this, and the other one happens to be, let's say, like this. In these two waveforms, don't you see their phasors will not be at the same place at the same time? Their phasors won't be at the same place at the same time. Like for example, if you show the phasor of this pink one, initially it was showing 0 value. That means maybe the phasor might be like this, sleeping, because their shadow will fall here. But initially the blue graph's phasor already shows some value. So maybe it was over here already, because you can clearly see certain value over here initially. Whereas for that pink graph, that is not the case. So what is there now between both of them? Over here in this diagram? That is delta phi, which is nothing but the phase difference between them. Both of them will be rotating with the same angular speed. Yes, they will be rotating with the same angular speed, but they will maintain their difference between their phases. I hope this is clear. So now going back a little bit in time and going back to this particular thing, if somebody had to draw the phasor diagram over here, will I not show the voltage and the current phasor together always? Check this out. Yes or no, my dear warriors? Check this out. So the length of the current phasor will be I0. The length of the voltage phasor will be V0. They will always rotate together. With the same angular speed. That's why they were in phase or same phase or no phase difference. Is everybody clear till this point? Happy Diwali, Kader. Clear, Sneha? Very good, Atluru. Okay, awesome. So that is the concept of phase difference and this phasor diagram. All right. So now let's go to alternating current with inductor and capacitor. Then we'll combine all three of them and then see resonance, impedance and all of that. So that's almost like the most of the chapter, and then the last concept comes as transformers. So when you take an inductor and then try to solve the question, then what happens to the graphs, etc. Let's have a look at it. Say for example, this is our source, this is our inductor, like this, L, all right. And let's say the current which is flowing in this case, the current is already known to me as I0 sine omega t, which means if I were to draw a graph, this is time for the current, because it is a sine graph, it will start from 0, reach maximum, reach minimum, reach 0, reach maximum, 0, minimum, and this will continue. This is how it will go for the current graph. If you ask me how the current phasor will look like, it is very obvious from here. That the current phasor, I don't know if I have so much space, but still I will use my liberties. And I will show the current over here like this. This is how the current phasor will be. It is at 0. So this is my current phasor, I0. This is my phasor diagram. This is my phasor diagram. Okay. Now let's try to find out the voltage in this case. Again, using Ohm's law or whatever. So again, let's use Ohm or Kirchhoff law. What do I get is this particular voltage which is there will be nothing but the current into resistance is what you will say. No, there is no resistance here. This voltage will be nothing but the voltage across the inductor. Whatever voltage is there here is also the voltage across the inductor. And I think I know what is the voltage across the inductor. It is nothing but L times negative di by dt, if you remember this from the chapter of electromagnetic induction. Voltage across the inductor is L di by dt with a negative sign. Correct? Oh, so can I differentiate this? Why not? So derivative of the current, which is I naught sine omega t, and L stays over here with that negative sign as it is. So what do I get? What do I get over here? I will get minus L. This I naught will come outside as it is. Derivative of sine is cos omega t. Don't forget, even omega's derivative will come. So it will look something like this. This is how the voltage will look like. Minus L I naught omega cos omega t. Okay, fair enough. Fine, sir. I am interested mainly in the magnitude. So even if that negative sign is there, I am not so bothered about it. Let's not get there. So if you just look at it magnitude wise or whatever, it's forgetting this negative sign, it is exactly this much. Now, usually I write voltage as current into resistance. So I will try to rephrase this entire equation like this. Voltage is equal to current into resistance. So my current is, let's say, I naught. Resistance is this whole thing, which is omega into L. And there is a variable term which I'm okay with, which is nothing but cos omega t. That is a variable thing. Okay, that's fine. Forget this for now. This is variable. Voltage is current into resistance usually. So current is I naught, voltage is V. Won't this term act like the resistance? Omega into L is looking to me like the resistance if I compare it with V is equal to IR. Forget this cos. So actually speaking, this term over here is like the resistance, but there was no resistance. So what do? It's like a substitute for resistance, but it is not actually, you know, the resistance. If you have played some cricket, football, etc., sometimes it happens. One player gets injured. Maybe that person was the fielder. So have you seen this or have you done this? You call one small guy, some junior, hey, listen, come over here, stand over here. What I have to do? You just come stand here. If the ball comes, just catch it and give it to me. You don't do anything. Just chumma, that person is like one, you know, dummy person. I think you too would have been some dummy like that, or you would have asked somebody, just stand over here. Just stand and just catch the ball and give it to me. That's all. You don't do anything, or just call me if something happens. So same way, this is acting like one resistor. It's like an imposter, but it is not a resistor. So it is not a resistance, but it is like a resistance. So we cannot call it resistance. So that's why we call it reactance. The symbol for that is X, because it is of an inductor, XL, L stands for inductor. So this is basically inductive reactance. This inductive reactance is omega into L. This inductive reactance is omega into L. So this is anyways cos omega t. Okay, I'm just interested in the magnitudes only, nothing else. So this is your I naught. So you can see this right over here, correct? So if I had to put V naught, V naught will be nothing but I naught. Maximum voltage will be I naught into XL. V is IR. What is V naught? V naught is this whole thing. This whole thing is nothing but V naught, which is the max voltage. Max voltage. V naught cos omega t. Right. So we got it in the Ohm's law form. And we can clearly see that the voltage is a cos graph. Voltage is basically a cos graph but with a negative sign. Usually cos graph starts from here, but because of this negative sign, I can just say it is probably, starting from the negative value over here, right? So that's all, guys. I can just say it is going like this, reaching like this, reaching like this, reaching like this, and so on and so forth. So that is how the voltage graph will basically look like. But this is considering the sign, but usually we are not interested in that sign, we are interested in that magnitude. So hence you will see, actually speaking, the voltage graph will look something like this. Will look like this. So now, is there a phase difference between them? Is there a phase difference between them? Tell me, my dear students. Is there a phase difference between them? Yes or no? Quickly think and tell me. Is there a phase difference between them? Yes, there is. Yes, there is. In fact, if you show the phasor of the voltage will be like this. This will be the phasor of the voltage. And you can see there is an angle between them. And yes, both of them are rotating like this with omega. So there is a phase difference, delta phi, of 90 degrees or pi by 2 radian. And who is ahead of whom? That is very important. The voltage leads, very, very important. The voltage leads by 90 degrees to the current. That is very, very important. Is this absolutely clear, my dear students? Yep. If somebody tries to calculate this quantity called as power, and you calculate the average power, believe me, the answer will be a big fat 0. Yeah, the answer will be a big fat 0. So there is no loss due to inductor. In fact, inductor acts like a storing device. If you remember, energy is always stored in an inductor, half Li square. It never loses energy. So an inductor never loses energy. Resistor will lose energy. That is what has been explained in all these questions and all these, equations over here. Okay. So this is what you should know regarding an inductor. I have made a beautiful slide for all of you. All right. So having said this, is there a question on this? Yes, there is a small question on this. You can see it right over here. Let's try to have a look. There is an inductor of 25 millihenry. Yes, the Henry is the unit of inductance. To a source of 220. Find the reactance RMS current in the circuit if the frequency is 50 Hertz. Frequency is 50. Omega will be 2 pi f, which is 2 pi multiplied by 50, which is 100 pi radian per second. That is first of all given information. Inductance 25 into 10 to the power minus 3 Henry. RMS value of the voltage is given to be 220 volts. Okay. All these are given information. First, can we find the inductive reactance of the circuit? XL. What is the formula? XL is omega L. XL is omega L. Omega is 100 pi. Inductance 25 10 to the power minus 3. So 2 zeros goes, this 10 goes, so it will be 25 pi into 10 to the power minus 1 ohms. So this 25 pi, if you multiply it, it comes out to be 7.85 ohms after taking this decimal also into account. So that is the inductive reactance. Yes, please remember the unit is ohms only. So the unit of this is a ohm. It is not anything else. It is like a resistance. It behaves like one. So the unit also is the same thing. So that is the answer. If you ask me the current in the circuit, the RMS current is voltage divided by resistance. But I don't have a resistance. So what I will do? I will take inductor's reactance. So RMS value was 220. Reactance was 7.85. So when you divide both of them, what do you get? Approximately 28 ampere. So that is your RMS value. Is that clear, my dear warriors? Very good. Now, moving ahead to the next concept is of the capacitor. Same thing you do it for the capacitor also. Same thing has to be done for the capacitor. So the next topic 7.5 is a source with a capacitor, and then they have done the same analysis over here. So my dear students, if you take a AC circuit with a capacitor like this, since it is alternating, current will go once like this, once like this. Okay, and this will be the voltage. Let us say our voltage is V0 sine omega t, which means on the time domain graph, our voltage will look like this. This would be V0. So we all know that for the capacitor, for a capacitor, the charge at any instant, the charge on it at any instant, let's say there is some plus q charge over here and some minus q charge over here, that charge will be nothing but the capacitance multiplied by the voltage. But the voltage itself is V0 sine omega t. Okay, so I'll put capacitance over here, and this is basically your charge. Now what I will do, I can find the current, which is nothing but dq by dt. So take the derivative of this. In this derivative, the capacitance is a constant, even the voltage amplitude is a constant. So the only derivative will be of the sine omega t term. Only derivative will be of the sine omega t term. What is the derivative of sine omega t? Let's find out. Therefore, the current will be, you have your capacitance as it is, you also have your voltage amplitude as it is. Derivative of sine is cos omega t, and that omega will come outside. This is what you will get. This is what you will get. But I don't like this form, so I will write it in a slightly more beautiful form, where current is voltage into resistance. Where current is voltage into resistance. Voltage by resistance, my bad. Current is voltage by resistance. So this is voltage, which is V0. That cos omega t is a varying term, so let's just forget about it. It's just a variable term, that's okay. C and omega are on the top. Current is voltage by resistance. So deliberately I will do one thing. I will divide this by 1 by omega c. Because if you take it on the top, omega and c will come over here in the numerator. Why did I do it deliberately? Current is voltage by resistance. This looks like resistance to me. So now my current will be voltage by an imposter of resistance, not a real resistance, but like a resistance. This is due to a capacitor. So an imposter like that is called reactance X, but due to capacitance, so C. And then you have that cos omega t, where your capacitive reactance, again the unit of that is ohm only. This XC is 1 by omega C. And you can also notice one more important thing. This whole thing over here, what you see, right? This whole thing over here, what you see, is actually I naught, some constant into cos omega t. So I naught technically is maximum voltage by the resistance imposter, which is capacitive reactance, just like the Ohm's law. Is this absolutely clear, my dear students? Okay, very good. So now, if you were to draw a phasor diagram, this is the reference line. My voltage phasor would be like this over here. My voltage phasor would be like this over here, which is a sine graph. The current graph is a cosine graph. The current graph is basically a cosine graph. So this will start like this. Oops. The current graph is a cosine graph, which will start like this. This is I naught. Here current is a cosine graph. Here earlier you saw the voltage was the cosine graph. So you will notice that the current's phasor diagram will be over here. This is your current phasor. You can see there is some angle between them, 90 degrees. Yes, both of them are still rotating with the same speed. They maintain their phase difference. In this case, obviously, the phase difference again is 90 degrees or pi by 2 radian. But here I will say it's the current which is ahead of the voltage. So the current leads whom? The voltage leads the voltage by 90 degrees. Current is ahead of the voltage by 90 degrees. Earlier it was the voltage which led the current by 90 degrees. So this is again very important. If somebody decides to calculate the average power, it will be 0. There is no power loss because capacitor again has the ability to store the energy. It will not cause any losses. So the power loss, just like inductor had no power loss, so here also the power loss will be a big fat 0. All right. So let's have a look at a question maybe. There are some questions over here. There is some capacitor, some frequency, find the reactance, RMS current, etc. If the frequency is doubled, what happens to the reactance and the current? Okay, simple guys. If frequency is given, omega is 2 pi f, 2 pi into 50, which is 100 pi radian per second. Talking about reactance, capacitive, is 1 by omega c. So 1 by omega is 100 pi. Capacitance 15 micro. 15 10 to the power minus 6. When you do the math, they have found out the answer. It comes out as 212, but this is in ohms. Then they have also asked what is the current in the circuit. In order to find the current, you will take the voltage and divide it by the resistance like thing, which is reactance over here. The voltage is 220 in RMS. Reactance, we just figured it out to be 212. This approximately has come out to them as 1.04, almost very similar, 1.04 amperes. That is the answer to the first part. Correct? Second part, what will happen to the frequency if it is doubled? Think about it. If frequency is doubled, then even omega will be doubled and it will be nothing but 200 pi radians per second. So because of which your XC, the new XC, omega is below, so it will be the old X divided by 2. Whatever was there, it will be divided by 2 because omega has been doubled. Numerator has not been changed. Denominator has expanded, so the ratio will decrease. So you will see that the reactance will become half of the previous one. So it will be nothing but 106 ohms. 2 and 2 will become 106. If you ask me what will happen to the current, what will happen to the current? Well, current is VRMS by XC. Resistance has decreased by 2 or half a factor. So RMS will increase, RMS current will increase 2 times. If resistance reduces, current increases, more current will flow. So whatever was the old current, it will basically increase. So it will become 2.08 amperes. Yes, yeah. They have also asked what is the peak. You can easily calculate it. If this is RMS, peak will be nothing but, if the peak current was asked, it will be root 2 times 1.04. They have calculated it to be 1.47 amperes if the maximum value was asked. That also you can do. Oh, thank you for reminding me for having water. I thought of giving you guys a break also now. I'll just give you guys a break. This was last example before we take a break, and then we'll again return. A light bulb and an open coil inductor are connected to an AC source through a key as shown. In the figure, the switch is closed. After some time, an iron rod is inserted in the interior of the inductor. The glow of the light bulb will increase, decrease, unchanged as the iron rod is inserted. Okay, so when you have an inductor, and let's say you have inserted some iron rod inside of that, what happens to the inductance? Can you guys quickly tell me what happens to the inductance? Yes, the inductance increases. Why? Because that rod is iron, which is ferromagnetic material. So mu, magnetic permeability will increase, more field lines will be there. So inductance will increase. It is ferro. Instead, if it was a diamagnetic material, no, then it would have decreased. Para will increase, ferro will increase, dia will decrease, di, go down. Paragliding, go up. Ferro, even better, you increase even more. So that's why it will increase, and because of that, what will happen to the XL value? XL is omega L, that will also increase. Because of that, what will happen to the current, my dear warriors? Current is voltage by XL. If this goes up, this will go down. So the current decreases. So current will decrease. That means the power of that bulb, which is there, which is I squared R, that will decrease. Hence, the brightness will also decrease. That is the answer. Hence, the light bulb brightness will decrease. That is a very interesting thing. Many people think it would have increased. But if the question said not iron rod, diamagnetic rod, then everything will be opposite. Permeability will decrease, L will decrease, XL decrease. So current increases, power increases, brightness increases. So a diamagnetic rod will increase it, para and ferro will decrease the brightness. Is this clear? Very good. So we will do this and resonance and transformers after a short break. It is not that difficult, but we will take a break. Meanwhile, please like the video in case you have not liked it. Like the video and also subscribe. Subscribe to the channel in case you have not done that. Okay, we'll just return in a bit. Hello. Yes, am I audible? Hi Krishna, Nicholas Latluru. Welcome back, welcome back, welcome back. And my AC also has stopped working now. Oh my god. So it's time to remove this. Okay. So welcome back, my dear students. It's time to talk about LCR circuits together. Before the break, we have seen that when you pass an alternating current through the resistor, the voltage and the current are in the same sync. They are in the phase, no phase difference. But the same thing if you do it for an inductor, you will see that the voltage and the currents are not together. In fact, there is a difference of 90 degrees. The voltage is ahead of the current by 90 degrees. Yes. And in the case of a capacitor, it is the current which is ahead of the voltage by 90 degrees. They are not in sync. And there is an imposter to the resistance, which we call as the reactance. For the capacitor, it is 1 by omega C, and current is voltage by that reactance for the capacitor. So naturally, same thing for the inductor also. There is inductive reactance omega L, and voltage is current into the resistance, right? That is what you have seen. Hi Ruthlessness, hi Mardai, good evening Sneha, good afternoon everyone, welcome back. Yep, all our regular students are back. So time to see LCR circuits and what have they explained in these three slides over here. See, the first slide they have talked about the basic circuit and how the voltages etc. will be written down in equation using Kirchhoff's law. The next slide they have done the calculations part of it, and they have introduced a term called as impedance, and finally they have drawn the phasor diagram and calculated the phase difference in general for the LCR circuit. Okay, so let's understand this. So you have an inductor, a capacitor and a resistor, LCR circuit, which is connected to a AC source like this. What will be same in all of them? What will be same in all of them versus what will be different is the voltage will be different, but the current will be the same. Whatever current will come, the same current will have to flow through the circuit. So the current will be the same. So I naught sine omega t will be same in all of them. So let's say over here, this is your time, this is 0. So the current graph is like a pure sine graph like this. Okay, this is your current graph. All right, I naught. If you talk about the phasor of the current, let's say it is like this. This is basically your I naught. This is the current phasor. Now, if you apply Kirchhoff's law, if you apply Kirchhoff loop law, you will see as you pass across the circuit, the voltage of the AC source, then over here, first drop you get voltage across the inductor, next drop voltage across the capacitor, minus voltage across the resistor. Finally, you will get this as 0. So if you move this on the other side, you will get the total voltage of the AC source is voltage across the inductor plus voltage across the capacitor plus voltage across the resistor. Now, voltage across the inductor is L times di by dt, right? Capacitor's voltage, Q is CV, so V is Q by C. That means it will be Q divided by capacitance over here. And across the resistor, it is just I into R. So this is what the equation will look like. Now we don't deal with the mathematics part of it. Don't worry about that mathematics, how to solve this equation, but this is how the equation will look like in case they ask you in your board exams, or maybe as an option in your NEET or any other competitive exam, right? So after this, when you solve this equation mathematically and get the final answer, that is what is more important to us. We get this voltage across AC, which we call it now as V. This voltage and this current, they are related as follows. They are related as follows. This voltage will be nothing but the current I naught into root of R square plus XL minus, or if you want I can write omega L minus 1 by omega C, this thing square, and here you get cos, or sorry, sine, whatever, because this was sine, so sine omega t plus, my goodness, sine omega t plus some delta phi. This is the solution that you get, and you will be wondering, sir, it is such a scary equation, but actually it is not. I will tell you why also in a bit. I'll explain everything one by one. If you just concentrate on this entire term, this is a constant term. This is some sine cos function. It's varying up and down. Forget that. This is that constant. So this is V is equal to something sine or cos. This something should be the amplitude. So this is your voltage amplitude. So this is nothing but your voltage amplitude. Voltage amplitude of that AC source. So that is basically V0, and this V0 is nothing but the current multiplied by that entire thing which you got over here, R square plus omega L minus 1 by omega C whole square. Now you might be wondering, what is this actually called? Is there a name for it? The answer is yes. This term is like resistance, but it is not resistance. V is IR. So all this thing in yellow is like resistance, but it is not resistance. It's a combination of resistance. Do you see what omega L is? And 1 by omega C is? They are reactances. So combination of resistance and reactance is then called as impedance. So our impedance is a combination, impedance Z is a combination of resistance and reactance. So it is R square plus, this one was XL, this one was XC, so XL minus XC square. This is what impedance is, and it is also expressed in ohms only. So V is IR is coming many times. You can write voltage is current into resistance, voltage is current into capacitive reactance, voltage is current into inductive reactance, voltage is total current into the total resistance, which is called as impedance. Everything will work. Z is the impedance. Yes. Now, if you have understood it till here, let me go to the next slide and explain to you. Actually, I have already created that next slide over here. Where do these impedances, voltages exactly come on the phasor diagram? That is very important. And what happened to the delta phi, sir? You didn't explain that. Hold on, I'm coming to that also. So first of all, if VL is the voltage across the inductor, VC is the voltage across the capacitor, VR is the voltage across the resistor, this V came out to be V0 sine omega t plus this delta phi. So if you start plotting the voltages on this phasor diagram, number one, inductor's voltage always leads the current. So the voltage across the inductor, I will show it like this. This is voltage across the inductor. Across the capacitor, the current is ahead of the voltage, or the voltage is behind the current. So the voltage across the capacitor, I will show it like this. It's behind the current. Remember, the entire phasor diagram was rotating like this with some angular speed. For the resistor, the voltage and the current are in the same phase, so might as well put it like this. So this is how I will put the voltage across the resistor. Don't you see they are like vectors now? One vector is here, one vector is here, one vector is here. You have to find the resultant of these three vectors to get our total voltage V0. To get our total voltage V0. If you notice very clearly, you will understand. I can actually draw a triangle like this with the base as VR, and VL and VC are opposite. If you deal with these two vectors first, one vector is here, one vector is here. The resultant of VL and VC, will be only this much, which is probably which is only this much, which is basically VL minus VC. I don't know who is big, who is small, so I'll put a modulus. Maybe VC is more, then this diagram will come down below over here. So then what I will see is the resultant of them is basically going to be V0. The resultant of them is going to be V0, yes, and this was 90 degree, of course, because this was 90 degree, yes, and this was also 90 degree. We have seen this before as well, correct? So this is how the vector addition of VR, VL and VC gives me V0. So technically speaking, this V0 vector is VL vector plus VC vector plus VR vector as vector addition. So basically phasors are added like vectors. Phasors are added like vectors. That's the advantage of treating them like phasors. That's the advantage of introducing that particular concept. So from this, if somebody asks you what is the magnitude of V0, you will use Pythagoras and immediately say it is nothing but nothing but this square, which is VR square plus VL minus VC whole square. You will immediately tell this square plus this square is this square. This is using your Pythagoras theorem. Individually, if you ask me this VL, VC, etc., I will tell, also keep in mind, on the next slide, maybe I can do this. Also, I can say this VR, VL, VC and this V0, all of them can be written down as, because the current is same, I can put I naught over here, I naught over here, I naught over here, I naught over here. For resistor, it will be R, V is IR. For inductor, it will be I into XL. For capacitor, I into XC. For total, it will be into Z. For total thing, it will be into Z. Similar looking formulas. V is I into Z. Same thing I have just written down here. These three things we had just seen before the break. Very, very identical looking equations. And since we have also told the total voltage is this square plus this minus this square, and before this also I had told Z is R square plus XL minus XC square, this looks very, very similar to me. Impedance is resistance square plus XL minus XC whole square under the root. Same thing, total voltage is resistance voltage plus difference of the voltage across inductor and capacitor square, whole thing under the root. Meaning, instead of VR, VC and all these things, imagine I had drawn a phasor diagram. Of resistors, then also I would get the same thing, my dear warriors. So I could have just said, listen, this is basically your current and I will show VR. Oops. Okay, anyways, I think I made a mistake over here. I should not have erased this slide. My bad. I should have done it on this slide. Yeah. Just 1 second. So instead of the phasors drawn for the voltage, I could have also drawn it for the resistances like this. So this is basically your I0, and along the current you will have the resistance in the same phase. You will have inductive reactance leading by 90 degrees to the current, and you will have capacitive reactance lagging. It is behind the current by 90 degrees. So this is XC. And if you take the vector sum of all of them, if you basically take the vector sum of all of them, so this was your resistance, this is XL minus XC. I don't know who is big, so I'll put a mod symbol. The resultant over here, this is basically your Z. This is basically your Z. Is this clear? So the same triangles can be also applicable for voltages or even for resistances and impedances. It is one and the same thing. It makes your job very, very easy. Keep this in mind. Now talking about the phase difference, which we were writing over here. Sir, what about this delta phi? This delta phi is exactly over here. So this angle that you see, my dear warriors, this is your delta phi, and clearly you can see if you take the tan of this delta phi opposite by adjacent, it is XL minus XC, whichever is big, whole thing by resistance. Or here also you can do the same thing. This same angle is there over here also. This is your delta phi. So tan of that phase difference between voltage and the current is nothing but again VL minus VC minus VC. I don't know who is big, so mod divided by your VR. This will also do. So this is how you calculate the phase difference between the voltage and the current. Remember, the current phasor will be over here. This is where your current phasor will be. Is this clear? These equations look very similar if you treat them like vectors. Main thing is this only. Voltages are added like vectors, even impedance is added like vector only. Think about it. So Z vector is actually R vector plus XL vector plus XC vector. But if you just look at the magnitude, it is this square plus this square. So R square plus XL minus XC whole square. So even it works for resistances, even it works for voltages. Current is common, so there is no equation like that for current. Current is the same because they are in series, one after the other. Clear? Very good. Now, if you ask me what is the power in this circuit, well. So many things I have to. Instead of that, I will draw only a new thing. That will be better. So when you have a LCR circuit, this was the voltage and this was the current phasor, this was the voltage phasor, this was V0, this was I0, and there was some angle between them, delta phi. If you now calculate the power loss in a LCR circuit, it will be the power loss in inductor plus power loss in the capacitor plus power lost in the resistor. If you remember carefully, I have discussed this. Inductor there is no loss, capacitor also there is no loss. It's only the resistor where there are losses, and that is I RMS square into resistance. If you remember this carefully, correct. So it is only across the resistor where the power losses happen. And you can do one thing, you can write IRMS square as IRMS into IRMS into R, and IRMS is actually IRMS is equal to VRMS divided by impedance. So that is what it is. I is voltage by resistance, but this is the total current. So total voltage by the total resistance, which is the impedance. Now I will just rewrite this slightly. So I will put VRMS over here, IRMS as it is, and then I will write R by Z over here. What is the reason for that? So this is the average power loss in your LCR circuit will come out to be the RMS voltage into the RMS current. What is this R by Z, you might ask? Go behind a little bit, see this triangle and tell me what is R by Z. What is R by Z? Adjacent by hypotenuse for this angle. So it is cos. Yes, it is the cos. So it is cos of delta phi. Correct. It is just the cos of delta phi. This cos of delta phi, whole thing is called as the power factor. It is called as the power factor. Very, very important. What is it called? It is called as the power factor. So you have two formulas now. You can write power as I squared R. So this is one formula. Or, so this was either I RMS square multiplied by the resistance, either this multiplied by the resistance, or you can use VI cos phi, but both of them should be RMS only, otherwise it will not work. So very, very important formula. Now, remember one thing, for a LCR circuit, if I draw a triangle like this, where this is VRMS, this is IRMS, and this is your phase difference, which is delta phi. So this is 90 degree, of course. This side is adjacent to the hypotenuse. So this is cos delta phi of VRMS into your IRMS. Same thing if you do it over here. This is opposite to the angle. So this is VRMS into IRMS, but into sine of del phi, if I make an imaginary triangle. This over here is the actual power loss, actual or real power. I hope you guys agree with that. This is the actual power which is being lost. This one over here is basically for a person who does not even understand that, hey, listen, there is something called as phase difference. So that person who does not understand AC will calculate this as the power without noting the without noting the phase difference. So that is called as apparent power. That is called as apparent power. This is called as apparent power without considering the cos of the angle between them. So the phase difference needs to be considered, or else you will get the wrong answer. So this is apparent. This is what you feel. This is what you think it is, but it is not real. It is actually this. This side over here, which you see, this one is called as reactive power. Reactive power. So very, very important. This power is basically the one which is oscillating between inductor and capacitor. Remember, inductor and capacitor cannot actually lose any energy. They can only store the energy. So when the inductor has stored the energy, capacitor does not have anything. Then the inductor gives that energy to the capacitor. They keep playing catch. Inductor will throw the energy, capacitor will take it. Capacitor will throw it, inductor will take it. They keep oscillating that energy between themselves. So that is why it is called reactive. Reactive elements means inductor and capacitor. Reactance. Yes. So it is oscillating between the inductor and the capacitor. It is not lost. It is just trapped between them, but it is not lost. It is not lost forever as heat. This is the one which is lost as heat, which is, usually consumed, usually lost as heat. This one is not lost as heat. This whole diagram is basically called as the power triangle. Sometimes they might ask you the question, what is the apparent power? What is the reactive power? What is the real power? What is the ratio of both of them? Anything such question might come on this. Clear? Very, very important. So all these things again are there in this whole thing over here. Now, there is a term called as a resonance. We will talk about it and then there are some questions on that. Okay. Now, you have your LCR circuit like this. You have a fixed voltage V0, maximum voltage, and then there is some current which is going over here. That current is I0 sine omega t. Okay. Now, imagine I calculate the current, maximum current which goes, which is nothing but V0 by your Z, but this Z itself has a value which is root of R square plus XL minus XC whole square. Just 1 second, guys. My dear students, I will be teaching in little bit of dark mode over here because what has happened is the lights are, UPS is blinking a little bit, so I might be using a little bit of dark mode. I can't turn on the lights. Electricity has gone, AC is not working, so I don't know how I will look, but it's okay. I don't know, it looks very weird right now, but I can't help it because I want to complete this topic. I don't want to leave this topic. Just 1 second. Okay. Fine. Okay. So I don't know whether you can see my hand or anything. Let's see if I can change some brightness setting over here. Okay, it's slightly better, I think. I just changed some camera setting, that's all. So I might look little bit weird, but that's okay. Okay, so basically we were just talking about this is how the current will change with this resistances. Now, remember, XL is actually omega L and this XC is nothing but 1 by omega C. That is what we know. Is that right? That is what we know. Okay, perfect. Now, if I change omega, this will change, Z will change, current will change. So if you plot a graph now, this is very interesting. If you plot a graph like this of the current which you get versus the angular frequency, how will that graph look like? That graph looks something like this. It is less initially, it goes up and then it again comes down. That is how the graph looks like basically. Wow, suddenly I don't know why I'm liking this dark mode. The screen looks so much nice and bright. At least I can see the screen over here. It is looking so cool. I'm not sure how it is on your side. Anyways, coming back over here, this is reaching some maximum value, like you can see. It is going up and then it is coming down over here. It is definitely reaching some maximum value, definitely. So if you see where it is maximum, like right over here, this is where the current I0 is maximum value. This happens at a very special value when both XL and XC are equal. Yes, I0 maximum occurs. If you want this current to be maximum, Z should be minimum, and Z is minimum when both of them are equal. That means they cancel out, it becomes 0. So there is nothing to add when this becomes whole as a 0. So basically, you will see XL minus XC is 0 or XL is equal to XC. So in general, I can say the value of Z is minimum. The value of Z is minimum and it comes out as R because XL minus XC is 0. 0 square is 0. R square's root is R. So Z becomes equal to R. XL value is omega L. XC value is omega C 1 by. So basically omega square is 1 by LC or omega is 1 over root LC. So this happens at a special value of 1 over root LC. That's when the current is maximum. This entire phenomena is basically called as resonance, or it has been tuned perfectly. It has been tuned perfectly. That is what it is. So your devices around you should always be in a resonance condition so that they function and deliver power properly, because that is the situation when current is drawn properly in that circuit. You have a washing machine, you have a TV. If the graph has not reached here, that means the device is not tuned properly, it is not resonating, it is not matching properly. So you have to add some resistor, capacitor or inductor so that it gets tuned and it behaves in sync with the AC source. And that's when it will draw very good power inside the circuit. And at resonance, you will see one more interesting thing which will happen. And because XL is equal to XC, think about it. XL phasor and XC phasor both are opposite to each other. Wow. XL and XC phasor both are opposite to each other. This was your current, by the way. This is how your current will be. So basically, they both get cancelled. They cancel each other. And because they cancel each other, you will see Z equals to the resistance. They have to cancel each other. So you will notice that in such a scenario, the voltage will be in the same phase because they both will cancel. Voltage will be in the same phase as that of the current, and you will see in such a resonating condition, the phase difference which you get is going to be 0. The power factor is going to be 1. This will be maximum power condition. Delta phi is 0, that means it is in phase. The voltage and the current are going to be in the phase. All these things happen together. Is this clear, everyone? Cool. So this is the condition of resonance which has been given over here also. You can see the same graph has been given. 1 by root LC is given, and yeah, everything else is as it is. So the power loss, or the power which is going to be consumed, which will be maximum, will be nothing but Vrms square, will be nothing but your whatever this voltage is, V0. So Vrms, you calculate Vrms square divided by R only, because R will be equal to your Z. R will be equal to your Z. Keep that in mind. Okay. So all these things are regarding your property of resonance. Keep this in mind. Okay. Perfect. Clear. Let's do some questions then, maybe which are there in your NCERT. Very, very direct questions are there. Like, see, a resistor is given, capacitor is given, they are in series, no inductor is there. Calculate the current, calculate the voltage across the resistor and the capacitor. Is the sum of the voltages more than the voltage? If yes, resolve the paradox. That's okay. All right. So resistance is given 200. See this. Resistance is given 200 ohms. Capacitance 15 microfarad, which is 15 10 to the power minus 6. RMS voltage 220 volts. Frequency 50 hertz. That is what is given. First thing, calculate the current. To calculate the current, first calculate the impedance. What is the formula for impedance? It is root of R square plus XL. Inductance is only not there, minus XC whole square. This XC is 1 by omega C. Omega, we already know 50 hertz, that means it is 100 pi into capacitance. Capacitance is 15 micro, so 15 into 10 to the power minus 6. Resistance already given to me, it is 200 ohms. So therefore from this you will get the value of Z, which they have calculated as 291.67 ohms, substituting all these values. Once you get the value of Z, calculating the current is not a big deal. So the current is nothing but the voltage by resistance, but in this case the total resistance. The RMS voltage was 220, impedance was 291.67. So solving this, they have found the current to be 0.755 amperes. But remember, this is RMS current, which is what is asked, I think. Calculate the voltage RMS, already it is given 220. Calculate the current in the circuit, that is also done. Then they have asked calculate the voltage across the resistor and the capacitor. They have asked calculate the voltage across the resistor and the capacitor separately. Okay. So here is the logic. The voltage across the resistor is current into the resistance. Current is 0.755. Resistance is 200. So from this, they have got the answer as 151 volts. Voltage across the capacitor is current into capacitive reactance, which is I, and XC is 1 by omega C. So current is how much? 0.755 omega 100 pi, and capacitance 15 10 to the power negative 6. When they calculated that, they have got the answer as 160.3 volts. Now, the interesting thing is, if you add these two voltages 150 and 160, it will go beyond 300, 100%. Definitely VR plus VC, which is definitely going to be more than the actual voltage of the source. This was given to me as 220. These both definitely, are more than 220 because this is 151 plus 160.3. 100% it is more than that. So is there something wrong that resistance and capacitance's voltages do not add to the total voltage? No, nothing is wrong. Don't get scared. Actually, if you see 151 square plus 160.3 square is actually 220 square. That is because they follow the phasor diagram, it is not added like scalars. So you should think of it like phasor diagram, where resistance is 151 volts, this is 160.3 volts, and this is 220 volts. Then it makes sense. Is that okay? So there is nothing wrong. Resolve the paradox. Voltages are added like vectors. Correct. Alex, first do easy problems. Solve the same problems which Sir is doing in the class, which Sir is doing in DNA batch, which Sir is doing in the RNA batch. Whichever solved examples are there, do that first. Then do laddu questions. Then do average questions. Then do PYQ questions. Don't jump to PYQ initially. And that's why I had told, use that NCERT based question book, which is your Tejas book, because that has very, very nice questions based out of NCERT. Every topic is there in this, physics, chemistry, biology, okay? And do it step by step. If you don't have Tejas book and you are in DNA batch, then you have access to many books in the pedagogy app. Pedagogy app, you can select easy questions only, moderate only, solved questions, unsolved but got it wrong. All those options are there in the DNA batch. If you are a part of it, you should use that feature. It's a very good feature. Okay, so do that and then slowly boost up your level and then reach PYQ. It's okay even if you are not doing it. Sri Hari, why are you taking class in Diwali also? My goodness, I should ask you the reverse question. Why are you asking this question right now? Why are you not studying in Diwali right now? I should be asking you a reverse question. Only the students and the teachers who are serious are still continuing the classes even in the holidays. I could have easily taken a break. 5 days, 6 days Diwali vacation. Nobody has done. Today also there is a class, evening Gopika ma'am's class is there, and again Saturday or something another class, Monday another class, yesterday also we had classes, day before also classes, Dashera also we had classes. We did not stop anything. It is continuing. The train is moving. If you don't catch the train, you will have to catch another bus, reach the next station and catch the train. If you miss that station, you have to catch another bus or you have to take a scooter or high speed scooter or car and go to the next thing. That means you have to put in extra effort, you have to spend more money, you have to spend more time, you have to do more hard work. Nobody is going to give you that super bike so easily. It is not so easy. So that is why better to go in a normal train which will take you peacefully without any tension. You don't have to spend more money, energy, time, anything. Got it? Yeah, right. So these kind of questions are there. Power, I think we just discussed all of this, right? So next example, power we have just done. Another example, a voltage is given, peak value 283, frequency 50, LCR, R, L and C are given, the impedance of the circuit. First thing, when you have to find the impedance, just use this formula, R square plus omega L minus 1 by omega C whole square. Resistance already given. How much is the resistance? Just check. Resistance 3 ohms. So this is already given as 3. This omega L, omega is 100 pi. So 100 pi into inductance. Inductance is 25.48. 25.48 milli. Milli means 10 to the power negative 3. This one, 1 by omega C, 100 pi. Capacitance is 796 micro. Micro is 10 to the power minus 6. Solve this, you get the value of impedance. They have got the impedance of approximately 5 ohms. So that's the answer for impedance. First part done. the phase difference between voltage across the source and the current? Well, the logic for that is voltage is like this, current is like this. This is your total voltage, and you have to find the phase difference, right? You have to find the phase difference. Another way of finding that phase difference is, okay, you know XL, XC and R, from that also you can get it. So draw a triangle like this. This is resistance, this is Z, this is XL minus XC. Resistance was how much? 3 ohms. Impedance was how much? 5 ohms. So naturally this will be 4 ohms. So naturally this is a very well-known triangle to me. This is a very well-known triangle, 3, 4, 5. So this phase difference will be 53 degrees. Directly you can get it. Yes, 53 degrees. Can you see that? 3, 4, 5 triangle. 3 was given to me, resistance is 3. Z we found out. Obviously this should be 4, na? This is right angle triangle. 3, 4, 5. Directly done. So phase difference calculated. The power in the circuit. For calculating the power, you use VRMS, IRMS into cos phi, or you can also use IRMS square into resistance. You can also use that, but the current is not known, so we can use this VRMS square by R. VRMS is maximum voltage by root 2 square into R. Resistance is known, voltage is known, peak voltage is given. Peak voltage is 283. So 283 square, root 2 square is 2, resistance is 3. This will give me a value of the power as how much? 4800. 4800 watts. That is the power. We can do that. If current was asked, if the current was asked, that also we can calculate. Current will be RMS value by your Z. RMS value is maximum by root 2 into Z. Maximum value 283. Root 2 is 1.41. Z value is 5. That value comes out as 40 amperes. So that is also done. Power is also done. Power we calculated it. What is the power factor they have asked? So if they have asked you the power factor, it is nothing but cos delta phi. Delta phi, what is delta phi? Cos delta phi. Just check this out. From here, this triangle only you can get it. 3 by 5. 3 by 5, guys. Yes, it is nothing but 0.6. It is nothing but 0.6. So this also we have calculated. Got it? How will you define impedance? Impedance is basically the net effective resistance of an AC circuit which incorporates the resistive and the reactive components like the resistor, inductor and the capacitor. And it is measured in ohms. So it again opposes the total current in an AC circuit. So it's the equivalent net resistance of an AC circuit taking into account all the 3 components. Is that okay? Palaniswamy R. Alright. Atluru clear. Jasmine clear. Sneha clear. Nicholas Tesla clear. Jeba, Krishna, Pranav clear. Awesome. Moving. Next question. Suppose the frequency of the source in the previous example you can change. You can change. What is the frequency for which resonance occurs? Resonance will occur at this frequency 1 by root of LC. So your L and C value is over here. L is 25.48. 25.48 milli. So 10 to the power minus 3. And capacitance 796 micro. 796 micro. So 10 to the power minus 6. So this value of omega based on that comes out as 222.1 radian per second. 22.1 radian per second, which is also 2 pi f. So if you do the reverse calculation, f will be 222.1 divided by 2 into pi, which is 3.14, which comes out as 35.4 hertz. So this is your resonant frequency. Resonance frequency 1 by root LC. Next, calculate the impedance, the current and the power at the resonant condition. So first of all, impedance at resonance is R, hence it will just be 3 ohms. Remember, R was 3 ohms, so at resonance Z is R, so it is just directly 3 ohms. What about the current? Well, the current will be maximum, and that will be Vrms divided by R. Vrms will be 293 by root 2. Why 293 by root 2? Because maximum voltage was, 283, not 293, right? 283 divided by root 2, and resistance was 3. That's it. That will give you the maximum current. So it comes out as 66.7 amperes. Compare it with the previous current. Earlier the current was 40 amperes. Now you can see it has increased. This is the maximum current you can get. You can't go beyond 66.7 in this example. What about the power? What about the power in that circuit? So the power will be again just Vrms square divided by R alone. Vrms square divided by R, or you can also use I squared R also, that is also okay. So this will be I max square multiplied by R. Power factor will be 1. The power factor obviously is going to be 1. So it will be 66.7 square multiplied by the resistance, comes out as 13350 watts, 13,350. Yes, 13,350. Earlier the power was 4,800. Obviously the power was less here. Now at resonance the power is highest. You can't go beyond this particular power. Is that right? Okay, very good. Awesome. So another example, this can be asked as a give reason or match the following phenomena, etc. At the airport they use metal detectors. What is the functioning working principle of a metal detector? What happens is, inside the metal detector, you will see it works on the principle of resonance of AC circuits. When you walk through the metal detector, you are in fact walking through a coil, inductor, capacitive coils are there, and the coil is connected to the capacitor such that if there is some metallic object, the frequency electromagnetic radiation which will come, which is reflected back exactly from the metal, happens to match with the resonant frequency. So when you walk through the metal in your pocket, the impedance of the circuit changes, and sometimes what happens is the frequencies are tuned very close to the frequencies which are reflected by the metal. So when you walk through that detector, because you are carrying a metallic object, that will change the inductance of the coil. It will change the total inductive property of the system, which will then affect the resonance. It will not resonate then properly. So because of which the current will change, and once the current changes, this change triggers an alarm, and that's why it will start beeping. So usually the coil will be in such a way that whatever electromagnetic phenomena is happening inside of it is tuned properly. It is properly giving maximum current. But the moment you walk with a metallic object, that metallic object will change the inductive property of the entire system, because that electromagnetic radiation will rebound and all of that, and that creates a change in the current. It will no longer resonate, and that's when changes in the current are triggering that alarm, and you will hear that sound. So this is another important example. This change in the current is detected, and the electronic circuitry causes a sound to be emitted. So when you walk through it with metal, your pocket, the impedance of the circuit changes, resulting in significant change in the current. So these are the important things which you should be aware of. Next, let's talk about transformer, which is the last part of this, which is basically the last part of it. A transformer was one of the greatest invention because Nikola Tesla again. This enabled you to increase or lower the voltage from any situation to any situation. Otherwise, it would have been tough. So this transformer made it possible. And a transformer is nothing but based on the principle of mutual induction. A transformer is based on the principle of mutual induction. Very, very important. Using the principle of mutual inductance. And it is used to change the AC voltage from one value to another value. If you remember mutual inductance, if you take a coil, pass some current, the current produces some field, that field goes through another coil and it produces electricity in the other coil. That is mutual inductance. So usually you have something called as the primary coil, you have the secondary coil. They are wound on a iron core because it is ferromagnetic in nature. And the reason why you use iron core which is ferromagnetic is because it will pass maximum field within the coil, or else if it is dia or some other thing, then the field lines will escape. Imagine there is current passing through the coil and there is no iron core. The field lines will go here, there, everywhere. But because of the iron core, which is ferromagnetic, which attracts the field lines, all the field lines will try to go through the secondary coil, thereby transmitting maximum flux and thereby improving the efficiency of the transformer. That's why you use iron core. By the way, all these things, Tesla got a dream and next day he just did it and it worked. Just imagine this. Just imagine he thought about this in his dream and he was able to do it the next day. He didn't know anything about transformers before that. He was the one who invented it. It is crazy to think about it. Yes. So you will see, based on the derivations and all of that, we'll come to it. If this is the ferromagnetic core, and let's say, okay, this is the primary coil, and on this side you have the secondary coil. There is the secondary voltage over here across this. This has N2 number of turns. This has some N2 number of turns. This has some N1 number of turns. Across this, the voltage is V1, which is also called as the primary side. The primary side. This is obviously called as the secondary side. Okay. Now, if you draw the magnetic field lines, because of the primary's current, obviously there is some current over here which is coming in from one side, and that current, when it goes through this coil, it is going to produce a magnetic field which goes like this. A magnetic field which goes like this, and most of the magnetic field will go through the core, through the secondary coil. Hardly any magnetic field lines will escape because of the ferromagnetic nature. Because of the ferromagnetic nature. Very, very important. You can see that right over here. These are the magnetic field lines. Magnetic field lines. So they will pass through the secondary coil. Now if you take any one of the primary coil and any one of the secondary coil, obviously there will be many such turns here also, and there will be many such turns here as well in the primary side. If a magnetic field line cuts through any of the primary coil, it will also cut through any such primary turn. Whatever field lines cut through any one turn will cut through every single cross section of the primary coil. Same thing will happen here. Whatever field lines will cut from the primary side will come back over here, and they will again cut through each of those cross sections or those turns. So can I say the flux per turn is the same for both? Is the same for both? Yes or no? Tell me this clearly. The flux per turn, is it not the same for both? Everybody agrees with this? Okay. And that flux per turn, let's say I call it as phi. Let's say I call it as phi. So if I calculate the total flux in the primary side, because there are N1 turns, won't the total flux be N1 phi? And on the secondary side, because there are N2 turns, won't the total flux be N2 phi? Won't it be N2 phi? Is that understood, guys? How N1 phi and N2 phi came? Very good. So now if I calculate this voltage on the primary side, this V1, won't it be rate of change of the flux on the primary side with respect to time, which is the derivative of the flux on the primary side is N1 phi. So it will be N1 d phi by dt. Same logic if I use for secondary coil, V by Faraday's law. How am I writing all of this? You might be wondering. I am writing this using Faraday's law. Faraday's law. The EMF induced is rate of change of magnetic flux. So this is d phi of the secondary by dt, which is the derivative of secondary flux is N2 phi. N2 bring it outside. So this is d phi by dt. Now what I will do, divide both of them. Divide both these equations. What are you going to get? V1, which has N1 d phi by dt, and below this I have V2, which has N2 d phi by dt. I am just dividing both of them, that's all. Oh, d phi by dt will cancel. So what will I get? V1, here N1, here I have V2, and here I have N2. That's it. They both are going to be equal. This number over here is also sometimes called as the turns ratio. The ratio of the turns, it's also called as the turns ratio. V1 by V2, primary by secondary voltage is number of turns on primary upon number of turns on the secondary. What this also tells me is, if by chance number of turns on the secondary is more than the number of turns in the primary, this has more turns, this has less turns, then the voltage on the secondary is more than the voltage on the primary. This is increasing the voltage from here to here. That is why it is called as a step up operation or a step up transformer. What is it called? It is called as a step up transformer. When number of turns on the secondary is higher and the voltage increases. The exact reverse is when number of turns in the secondary is less than in primary. So the voltage is less on the output side. So this is bringing down the voltage. So it is also called as a step down operation or a step down transformer. This is called as a step down transformer. Is this clear, everyone, till this point? Got it? Now, where the power is generated in a hydroelectric plant, you have a step up transformer which increases the voltage, and outside your house that voltage is brought down to normal voltages. That is what usually is basically done. So wherever your electricity is generated, AC is generated over here, you will see it will enter you will see that it will enter a step up operation. You will see that it will enter. This is the symbol of a transformer, by the way. This is a step up transformer, and this voltage is then carried, the higher voltage is then carried using transmission lines, okay, using transmission lines from one city to the other. You might have seen those big transmission towers. You might have seen those big transmission towers, right? So using those transmission towers until you finally reach the destination, and you will see when outside your house, what happens is you have another transformer which is a step down transformer. Step down transformer is used, and finally it enters your house. It enters your house. So here the voltage might be some 10-20 volts. It is taken to some 20-30,000 volts. Again, it is brought to 220 volts. So usually it is 220 volts here. Usually in the transmission line, it is 22,000 volts over here. And here it is very, very small. It could be some 10-20 volts also. Maybe it is 22 volts or something like that. Very small voltage is generated here. Example, okay? So this is just an example given to you. So step up, taken like this, step down. Why is this done? The step up process, this is to reduce the I squared R losses. So what happens is the current which is there, the current will reduce. So I squared R power losses are made minimal because of this operation. So very negligible power is lost in that transmission process. Clear? Everybody with me on this? Okay. Awesome, awesome, awesome. All right, all right, all right. Okay. Now, having said this, you should also know one thing. For almost 100% efficient transformer, the power on the output side, that is the secondary side, and the power on the input side will be equal. No power is lost. So input power will be basically V1 I1, and output power will be nothing but V2 I2. So therefore, from this, what do I get? If V2 is below, I2 will go on the top. If V1 is on the top, I1 will go below. That is what I will get. And if I recollect clearly, V1 by V2 was N1 by N2. So what you will see, this thing was actually speaking N1 by N2. So you will notice that when voltage increases, current decreases. When voltage decreases, current increases. Yes, it is inversely related. So in a step-up transformer, the current on the secondary side will be less than the current on the primary side. And in the step-down transformer, because the voltage reduces, the current will increase. So I2 will be more than I1. So it is exactly inversely related to each other. Very, very important for a 100% efficient transformer. But usually there are some losses which occurs, and the losses which occur are given to you on this slide. The equations obtained above are for an ideal transformer without any energy loss. But there is a but. What is that but? In actual transformers, some energy is lost due to the following reasons. First reason why the energy is lost is called as flux leakage, meaning you will not see all the field lines going through the secondary. Some of the field lines might get lost somewhere over here, might go somewhere here. So flux leakage will happen. So to prevent that flux leakage, you use a very good ferromagnetic material. That's why you need a very good ferromagnetic material, and the coils have to be tightly wound. This is the first reason. The second reason, so there should be no air gaps. So the design of the core should be such that the design of the core and the air gaps in the core should be properly maintained. Winding should be proper. The second reason why this happens is the resistance of the winding. The winding itself has some conductor wire, so the wire itself has some resistance. So you use a wire with low resistance to reduce the loss. Third loss is eddy current loss. Eddy current loss. Yes. Remember, when currents producing magnetic fields are changing, the changing magnetic field creates current loops, which creates more heat loss. So that loss is also there. Also, last loss is hysteresis loss. Oh, by the way, before we go ahead, remember, to reduce eddy current loss, you use a laminated core. If you laminate that core, then you will see that that lamination prevents those eddy currents which are formed. Yes. Last is hysteresis loss, because the current is alternating in nature. Because the current is alternating in nature, the field will keep reversing. The core will get magnetized, demagnetized, magnetized, demagnetized. So there is a hysteresis loss in this particular process. So that can be reduced by using a core with low hysteresis loss. You keep it minimum by using a material with low hysteresis graph. Then the hysteresis losses are also kept minimum. Okay. So this is very important, and this paragraph I have already explained over here. So step up and step down transmission, this paragraph I have explained over here. This is the transmission line which goes from your house to your power generator. Okay, so that comes down to the summary part. Yeah, voltage and currents in AC generally may not be in the same phase. There might be some phase difference. And current in general is voltage by the resistance, but the resistance will change depending on whether there is an inductor, capacitor, or a combination of these three. That value of the current or voltage which behaves like the AC and produces the same power is called RMS. RMS is maximum by root 2 or 0.7 times the maximum value. And you can directly use power is V square by R, I squared R, where I and V are the RMS values. Those are those equivalent values which produce the same losses. Correct? For resistor, voltage and current are in the same phase. For inductor, voltage is ahead by current by 90 degrees. For capacitor, it is behind the current by 90 degrees. Capacitor and inductor never cause loss. It's the resistor which causes the loss. Capacitive reactance is 1 by omega C. Inductive reactance is just omega L. We have seen that. And impedance is the combination of resistance and reactances. Reactants are like imposter. They are not real resistors, but they behave like resistors. Same units. So when you combine both of them, you get impedance. When you write power, power is voltage into current into cos. You can't just write voltage into current because there is some phase difference. You have to put that cos. That cos is called as the power factor. In resonance, the power factor is 1 and power lost and energy consumed or current is all maximum in nature. That is called as resonance. And for a transformer which is ideal, where you can minimize the losses, flux loss, hysteresis loss, eddy current loss, or the wire windings loss, you minimize it. V1 by V2 is N1 by N2, but current wise it is I2 by I1. That is what you will see. When the voltage increases, it is called step up. When the voltage decreases, it is called step down transformer. Okay, that is what is there in the summary. We also seen the power triangle where Vi is apparent power. You will also see the base, which was Vi cos phi, is the real power, and the reactive power is basically your current and the energy which is not actually getting lost. It is just trapped between inductor and capacitor. That is called as your reactive power. Also keep in mind the current which is there in that triangle, that also has a name. I can give you that name also. This current, just this much current which is there, just this much current which is there, this is also called as wattless current. Wattless current. I sin phi. I sin phi is also called as wattless current. I sin delta phi is also called as the wattless, meaning no energy loss. Power is lost, actual power, watt is consumed. Here no watt is consumed, no loss happens in reaction, reactive. So wattless current, that is what it is called. Okay. So these were the things, and if you are done with AC, make sure you put it up in the comments saying AC is done. Okay, and if you loved the class and you love the dedication that I show towards you, no matter whether light is there, whether I am sweating or not sweating, make sure that you are not only subscribing to the channel and liking the video, but talk about this channel, talk about the teachers here, because we are working really hard for you. Whether it is Diwali, whether it is Christmas, whether it is a vacation, whatever it is, we are there with you. Thank you so much. Have a great time. All the best, and put in the comments AC done. Do not forget to like, comment, subscribe, and talk about this channel. All the best. Take care. Bye-bye.